Alright, so to talk about the decay lights and the closed auctions, and very briefly, which is some of the very important part in the particle physics to observe some of the observable, the decay light, as one of the lifetime, and the closed auctions as effective area. And such the key points of the two objects is the decay light and the closed auction, the proportional to the probability as a scale sort of the Earth matrix or amplitude, which can obtain from the Feynman diagram. That's a key point of the slide, and always talks about the very brief physics implication rather than some of the details calculations. So first of all, it starts from the Fermi's golden rules of the time-dependent perturbation in the quantum mechanics. The Schrodinger's equations can be written like that, with the perturbing Hamiltonian, and if we insert that the wave functions, which expands with the energy eigenstyles with the time dependence coefficients, and we can find the equational motion for the, such a time dependence coefficient from the Schrodinger's equation. And the solution of such a time dependent coefficient is given as some of the evolution factors with the energy pace and the transition amplitude, which is acting through linear styles and going to binary styles with the interaction perturbing Hamiltonian. And the probability is just a scale of the such a time-dependent coefficient. So the is mean that the probability from the initial I state to the final up state with the transition amplitude and the also the phase factors with the energy. And such a phase factors becomes some of the energy conservation and the phase factor in the limits of the time goes to the infinity. And actually we can have signed the Fermi's golden rule. The one part of the Fermi golden rule is the transition amplitude, the case of transition amplitude as the probability, and the other part is the phase space and energy conservation, and it gives event light or decay light. And also we can use such a perturbations regime if we insert the solutions again in the equation of solutions, such as solutions, and insert such solutions in the equation of motion, and then we can also find the second order terms as intermediate size of the k and the denominators with the difference of the intermediate size energy and the intermediate size energy. So now I turn to the second part, the decay light. The decay light case. The record parameters are given by the two-part phase space and the scales of the transitions and amplitude. And the first part phase space can be written as energy conservations, and then we can change the variable from the energy to the number density. And such a number density can be written in the momentum space in the as some of the phase part and the momentum conservations part. So the Fermi rules can be written with the momentum space, the pages part, and the for momentum conservation part. And the remaining part is the transition amplitude, and we want to make sure what some of the Lorentz invariance amplitudes in the relativity theory. And the actually Lorentz invariant normalizations are given by the normalizations of the wave functions as a 2e factor, so that the such a phase pi sort of e primes is actually Lorentz invariance quantities under such a transformation. So there's one important result of the discussion that formula for the decay light is given like that. First of all, there's a scales of the Lorentz invariance amplitude, also called S matrix, which can be obtained from the Feynman diagram. And there's a full momentum conservation, and the phase space factors and the accelerator Lorentz invariance factors are multiplicated. And also there are some of the binary state phase space and the initial particular energy or the mass in the last prime, such a factors are also multiplicated. And such is the decay light, inverse of such a decay light is a lifetime as the dimensions of the time. So I will turn to some of the very important examples of two-body decay. Particle A is the decay to the 1 plus 2. recall that in the relativistic energy momentums and the mass relations E scale minus P scale are equal to the norm scale. And in the special case, in the mass last case, the right hand side is equal to 0, so the energy and momentums are same. And in the last prime case, the 1, 3 momentums are equal to 0, so the energy and the mass are the same. But in the general case, the energy are written by the 3 momentum and the mass. And we will start the initial particle ice in the last prime, center of the mass prime. So the energy of the particle A, initial particle I, is the same with the mass of the initial particle I, and the 3 momentums are equal to 0. In this sort of the momentum conservation part can be written like that. The initial particles are amazed and the initial momentums are equal to 0. So and by using the delta function, we can ignore the we can remove the second momentum P2 as minus P1 like that. And in the first momentum P1 final state, the can be written like that as particle coordinate. And the in the inside part, such a part can be changes as a variable to the E. Then the from the P1 to from the P1 to the DE energy, then the such a Jacobian such a change of variable factors like given like that, which is very similar to the such a E1 and the E2 phase space Lorentz invariant factor. So I will skip the calculations. So the change the variable from the P1 to the east has such a factors and such some of the very similar factors that appears here. So we can calculate like that. There are some of the additional factors that you want to know too. And the delta function for the energy part, MA is should be equal to the E. So that there are additional MA factors that appears in the denominator. So in the divided decay with the center of the mass prime, the decay light is proportional to the one of the MA scales and the amplitude scale. And there's such a P scales that are some of the binary momentum side. This is a very simple calculation for the two-body decay case, and in the three-body case, there are some of the more complicated because there are more energy and momentum freedoms in the conservation condition. So there are appears there are some of the inequality conditions. And now I turn to some of the cross-section part. Part of the picture is dry. The relation between the decay light and the cross sections like this. There are some decay light in the left side with as a sort of inverse of time, and the cross sections the area, so the x scale. So if we multiply the number density, one of the x cube as a volume, one of the volume, and the v particles velocity, then the dimension analysis, there's much, and also the physical meanings are also same. And we set the number density equal to the 1 because we only see the some of the one particles scattering, two by the two scattering. So cross sections given by the decay light was the relative speed between velocity between the binary particle. So the only difference that initial factor initial velocity factors that appear, and we can change this factor to the Lorentz invariant quantity by using some technique. There are some of the such a factors we set up, and there are some of the calculations of the VI to the other momentums and energy quantity expressed as momentums and energy, and the upscales written like this, and the upscales can be written as only by the Lorentz invariant quantities, momentums and mass. So the binary just given like that, and the please follows yourself. As a Lorentz invariance factor. Also similarly we can apply for the CM primes 2 by 2 scattering. There are initial particles that is as A, B, and the final particles 1 and 2, and we also CM prime. So the initial particles momentums has a PM equal to minus PB relation. And the Lorentz invariant factors up is reduced into the S channels momentum transfer root S as a summations of the center of the mass energy. So the difference is the mass of the initial particles in a decay light is replaced to the center of the mass energy S in the cross section. So the in the same primes, the cross sections are given like that. So it just changes from the MA to the loose S. And also we can use some of the differential cross sections as the functions of the angle and the energy, so-called the angular distribution and energy distribution. And the momentum transfer in the T channel so can be expanded by using the just simple calculations. And if we assume that the 1 and the 3 particles has some of the angle theta between the P1 and the P3, then we can change the omega solid angle to the dt, where the t is the momentum transfer in the T channel. So that we can obtain the differential cross sections in the energy distributions. And actually, this is the Lorentz invariant in the any primes, such a formula can be applied. And also there are some other complicated cross sections in the lab primes, but I will skip about here. So the key points of the today's discussions, the observable in the particle physics, the decay light as the inverse of the lifetime, and the cross sections as a effective area. And the decay light and the cross section is given by the squares of the amplitude asymmetry, so which can be explained in the Feynman diagram. And also we should integrate over the all possible state, which is expressed as the page space. And also the such a decay light and the cross sections, they can be expressed as the functions of energy or the angle, so angular distribution and distributions, and also the resonance can be pierced in the heavy particle, and we'll discuss it in the following particle phenomena in the other video. And the other one I want to mention, one more thing, the event light is given by the multiplication of the cross section and the luminosity L. The cross section is some of the probability, and the luminosity is how much we repeated such experiments. So I will finish the slides videos.